knew she was signing up for like the whole day. I was like, you know, it's going to be the whole day. It's going to be a big day. Me too, Mom. So, you know, I'm sure that I was bored going to my mom's office and but I still have like super warm memories. Yeah, 100%. I had no idea what was going on in the chemistry in my mom, so I wouldn't get mad at her. So. Holy cow! You're like a younger. You're like Matt. You're like a young person.
Digital devices and stuff like that. Yeah, really? I still do paper. Okay. It's just.
All right, everyone.
This is the fix.
Let's go ahead and get started. Good morning, everyone. It is my pleasure to introduce Dr. John Albers. John is a research physical scientist at NOAA Physical Science Laboratory. And he focuses a lot on subseasonal to seasonal variability and predictability. Prior to that, he was an alum here. He graduated from our undergraduate program, class of 2005. He was an AOS major and an applied math major, which is clearly the reason why he is so successful today. After that, he went and did a PhD in atmospheric science at UC Davis, and then a postdoc. He was an NSF postdoc fellow at CSU at Colorado State University, and that's where we met. I was a graduate student at the time during his postdoc. And then after that, he was at CIRIS, which is the Cooperative Institute, the NOAA Cooperative Institute with the University of Colorado in Boulder, and he was there until 2023, when he began his job at NOAA PSO. So thank you, John, for coming. It's great having you here, and without further ado, I'll let you take over.
Awesome. Thanks for having me. I'm super excited to be back here. First of all, I just want to point out I'm here as a alum, not as nothing that I'm presenting here you should take to represent views of NOAA or anything like that. I'm really here as a private alum giving a talk. So I just want to make that clear. I actually have a lot of roots here. I'm really excited to be back. I grew up on campus here. My mom had a lab over in Chamberlain Hall, and my brother got his undergraduate degrees here, his PhD here. My wife got her master's and undergraduate here. So it's like super exciting to be back. I wanted to do this for a long time, so thank you to Steph and everybody else for having me. So my background is actually more in a applied math side of atmospheric science, so I don't know if I said asymptotic analysis, WKB theory, are there any hands in here? Michael? Yeah, okay. All right, how about this? This is some homework for the 610, 611 people. I bet Uncle Chat can, how about this? Let's start with this. Who derived the QG equations first? No faculty. Yeah, Dan. Anybody? Oh, you guys are making your faculty sweat. All right, so Jewel Charney. All right, so he did that with scale analysis, and then his student, Joe Podlasky, did it with asymptotic analysis. I bet if you ask Uncle Chat to derive the QG system with asymptotics, I bet it spits it out. So there's your homework for 610. So who's teaching 610 right now? Mike?
That's not their homework.
That's not their homework.
But it will be on the exams.
There you go. All right, so that's kind of the world I come from. I don't come from a forecasting world at all. The last time when I was a grad student, the last time I had forecasting stuff was in Professor Martin's class doing, the forecasting contest or whatever in 452, which you still do, yeah?
Yeah, you did better than I did.
Boy, I don't know about that.
It's not a high bar, though.
Yeah. However, when I started working at NOAA and Series, I started interacting more with forecasters, and maybe, I don't know, 3-4 years ago, I started attending the operational subseasonal discussion every Friday morning, and it was a real eye-opener for me. Their job's really, really hard. And a lot of the tools and things that those of us that are more in the academic or theoretical world are building may or may not be super helpful to them. So what I wanted to do today, I have some of my results towards the end of the talk, but the first half of this talk is really just talking about what a subseasonal forecaster goes through, and I'm going to try to communicate to you what are the types of issues that they have, and how might you all, i.e. students, come up with ideas that can help those type of folks improve their forecasts. All right, so just to begin, for those who don't know, this is the CPC landing page. And on the left, you'll see the different forecast products, right? It starts with 6 to 10 day outlook, 8 to 14, 3 to 4, weeks 3 to 4. And you'll notice that the 1 month on the right, the averaging period is getting larger, right? And it's not because we don't want to predict daily weather, but it's because we can't. And so you have to take longer and longer averages, okay? I'm primarily going to be talking, everything I show today are going to be, you can assume, are weekly averages, right? But really, this is really focused on the weeks 3-4 time period. So just kind of keep that in the back of your mind. All right, so skill is really low, starting at about week 3. And just how low? What I'm showing here are, this is for the European Center IFS for a reforecast period of about 20 years, and I'm showing the forecast skill score via the anomaly correlation for 500 millibar heights. And what you see on the left is it's totally saturated, and that's because the skill, so for those of you who don't know, the IFS is like the gold standard. It's the best model in the world. It's better than NOAA's. It's better than everybody else's. So this is as good as it gets. Week 1, skill's great. It's anomaly correlation above 0.9 for sure, right? So no problem. Week 2, you're starting everywhere still above 0.5, which is, it may not sound great, but for these time scales, that's great. If we could forecast 0.5 out to weeks 4, we would all be ecstatic. However, starting at about week 3 and really dropping off at week 4, anomaly correlations and, for all variables, temperature, precip, anything we care about, you're dropping down into the 0.2 to 0.3 range, right? And I know that's sort of abstract, so what I've done here is for each of these skill categories, I've just plotted some maps, and the forecast lead that these are for, it doesn't matter. I pulled them all for week 4, but that's not the point. What I really want people to walk away from here is, what does a geopotential height map, anomaly map, look like for these categories? And it's really going to kind of nail home why the week 3 is such a problem. So on the left panel, I'm showing an IFS forecast. And on the right is verification from JR 55, and that has a pattern correlation of somewhere around 0.9. And you can see that it's really pretty good. The highs and lows are in the right places, amplitude's fairly decent. If you were a forecaster, you'd be ecstatic about this. This is from the '98 El Nino season. This is when we were mistakenly convinced that we were going to be able to successfully forecast on subseasonal timescales. And it wasn't until we've had data for another couple decades that we realized that that's not a canonical ENSO, that's like the anomaly ENSO that we wish we had every year. All right, so now let's shift to 0.5 correlation. Here, it's still pretty good. Amplitude's low, but at least the wave pattern's in the right place, right? If I'm on the East Coast, if I'm in the Pacific Northwest, at least I got the fact that there was a low coming on shore, right? This probably came out of the Gulf of Alaska or something like that. It's late March, or mid-March. And the high pressure systems are in the right place. This is pretty good. It's not perfect. If you live up on the north slope of Alaska, it's not so great. You missed that a little bit. But overall, this is a pretty good forecast. This is usable. If you're an end user, and this is good. However, that's not where we are at weeks 3-4. Generally speaking, we're in the 0.2 to 0.3 range, and this is high point, right? This is closer to 0.3. Often we're way worse than this. This is not useful. If you live in the Pacific Northwest, the forecast is telling you got high pressure. It's going to be sunny and nice, and clearly what happened was something came out of, it's coming out of the Gulf of Alaska. It's wet. So this is not a useful forecast. But this is the norm. This is what they're dealing with on a daily basis. All right, so given that this is what the skill environment and ensemble prediction system looks like, how do forecasters deal with this? What they try to do is they get the multi-model ensemble guidance, and I'll show that in a minute, and then they're kind of doing like their own human machine learning with climate indices and things like that. Like I know the state of ENSO, I know the state of the MJO, and you're trying to extrapolate what the forecast guidance looks like and whether you can believe that. And I'm going to kind of step you through what a forecaster would do. So, you know, in the winter, the kind of teleconnections and predictable signals that we don't have a lot. We've got ENSO, sudden warmings, those are, you know, once every couple of years. The MJO, the QBO, I originally was trained in stratospheric dynamics. I would love for the QBO to be helpful. I'm yet to be convinced that it is helpful. It's a wonderful fluid dynamical phenomena. And maybe someday we'll figure out how it's useful. I think maybe it does seem to shift the probability of a sudden warming, and that may be helpful on a seasonal timescale, but for subseasonal timescales, I'm a little dubious. Possibly soil moisture. People are proposing this in the summer, right? The waveguide across the Pacific is not so great in the summer, and so you know, these other pieces are not so helpful then, and maybe soil moisture gives us some memory, but that remains to be seen. We're still trying to work that out. All right. So what do I mean by predictable climate signals? I know not everybody, I think that, you know, when I was an undergrad, I didn't know what the MJO was, I'll be honest. So what is it? So this is just a quick crash course. So on the left, I'm showing maps. If you can't see the underlying map there, that's essentially over the maritime continent, right? And the MJO is a propagating OLR wind pattern, and as it propagates through I'll define what the phases are in a minute. It propagates eastward, right? And with that, there's divergent outflow. That's a Rossby wave source. And that excites downstream teleconnections or Rossby waves, which I'm showing on the right there. And I did not give proper credit to Steph Henderson. Later on, when I show this figure again, I properly cited Steph. So Steph, I'm sorry. That's from one of her papers from graduate school?
Yeah.
Yes, okay. And what you're seeing there is, if I recall correctly, it's like 250 millibar heights. That's the wave train. And the color filled contours, I think, are maybe GPCP precip or something like that. And that's for phase 3. So you have this downstream teleconnection. With that, you can build historical composites for the different phases of the MJO. And the different phases are just where it is in the tropics as it moves eastward. And you get these different temperature anomalies with them. Some of them are cold, some of them are warm. And you kind of log that into your head. Okay, so you know, there's some sort of downstream timescale associated with that. We get Rossby wave forcing in the tropics, and then, you know, some days later, you get a wave train that arrives over North America, and you get a temperature signal that's associated with it. Okay, so how does a forecaster turn that into something useful? What they do is they plot this on a dial, and essentially this is just a phase diagram. They have 2 indices of measures of the MJO, and it's essentially a phase plane where it traces out the amplitude of the MJO and where it is in phase space, right? And those phases are just different parts of the tropics. Excuse me. Here you can see that the initial forecast guidance, the ensemble mean is that lime green color, and all those little yellow lines are the different ensemble members. And what it's showing is the initial condition is somewhere in the Indian Ocean, that's phase 3, and in this case, it's tracing itself out and ends up somewhere in the Western Pacific. So that dial on the right is what a forecaster will use when they show up on Friday morning. They've got an hour to look at the guidance and issue a forecast. All right, so what do they get? So the first thing that, you know, is going to pop up is they'll have ensemble guidance from at least 3, if not maybe a couple more of the major forecast systems. Generally, the CFS, the IFS, and the JMA, which is the Japanese model. These are, on the top, I'm showing 500 millibar height anomalies. And these are for the ensemble mean, right? So each of these models has a different number of ensemble members. CFS is, I don't know, it's changes. I don't know if it's like 50 now. The IFS is like 100 or something. But those are the ensemble means. And then on the bottom are the 2 meter temperature anomalies that go along with it. So if you're a forecaster and you look at this right off the bat, it's, you know, you don't have a lot of agreement there. It's hard to know what to do with that. If you look at, say, the bottom right 2 panels, right, the JMA is predicting kind of cold over the Great Lakes and in that part of Canada, whereas the IFS is doing warm temperatures. So, you know, and the converse for the Southwest. So, okay, that's some information. So then they'll turn to the MJO index. And they'll trace that out and they'll calculate where they think they should be, where we're initializing, where that's propagating to, and what that is from historical records. You go, okay, in the historical record, phase 5, 4, 5, and 6 would be warm around my forecast verification window. If it propagates fast, if the jet waveguide conditions are different, if the tropics lend the MJO to propagating different, maybe it's a little cold. But mostly we're probably getting an idea that there's gonna be a warm contribution from the MJO out of this. Okay. This particular forecast, which was issued on December 1, there was an MJO going on, and I'm showing the expectation that you would get from the MJO. ENSO was going on as well, and what I'm showing there is that's just a historical correlation map between the Nino 3.4 index centered in December and the temperature anomalies over North America, and that you would expect on its own to give warm temperatures, that's yellow, over most of North America, and on the south, a little bit of cooler temperatures. There also happened to be a reasonably strong NAO going on, and so that is also kind of contributing to warm temperatures across kind of a similar region. Now you grab the ensemble mean guidance. So in this particular case, they took the MLR is their multiple linear regression model. That's a statistical model that's got ENSO and MJO and trend in it. And that gave something similar to this. It'll give you the ENSO and MJO. They blended it 30% IFS, 25 CFS, and 10 for the Japanese Meteorological Association. By the way, if in doubt, you go with the IFS. That's just kind of the rule. It's just better than everybody else. So that's kind of how people lean. All right, so you look at this, and maybe it's not so bad. Some of the models are, the operational guidance, right there, may be a little different. However, when you look at the predictors, ENSO, the MJO, the NAO, they're all kind of suggesting maybe there's going to be warmth over the northern and eastern tier of the US. So then the forecaster takes this, and this is just what's called the auto blend. So this is just they take those percentages that come out of the ensemble forecast system and you add them up. Then the forecaster draws, they might adjust it a little bit. That's the middle panel. That's the official guidance that came out. And they might adjust it a little bit. Here, the forecaster was less certain about that cold anomaly down in the southwest of the US, so they put equal chances there. But everywhere else, they kind of put warm. On the right, I'm showing what the verification was, 3 to 4 weeks later. And that's a pretty good forecast. You're probably looking at that and you're going, well, they didn't get California and the Southwest right. Alaska wasn't so great. I'm here to tell you that that's actually a pretty good. If you're a forecaster, this is pretty good. This is about as good as it gets. Okay. You had a forecast, you had predictors. Maybe we're making some progress here. Okay. A few weeks later, December 22nd, just 3 weeks later, same ENSO conditions. So I'm showing the SSTs there on the left for the month prior to the two initializations, right? The first one was December 1st. This one's December 1st. This one's December 22nd. So we're thinking kind of a similar. And so now the computer model guidance, everybody's in agreement. You're a forecaster, you're like, all the models have locked onto the same pattern. That looks like ENSO. We're starting to get more into the winter season when the Pacific waveguide is maybe acting more like we expected to. This is an ENSO teleconnection. All the models are locked onto that. And if you notice the confidence in the guidance, right? This forecaster upped that guidance quite a bit. All the models are in alignment. How did it work out? Oof. Just brutal, right? There's nothing happy about this. Even the little bit of Alaska where you thought you had warmth, that was actually neutral. So there isn't a place on this forecast map where things worked out. That I don't know what to say. If you're a forecaster, this is just bad luck. Like, I wouldn't have done anything different. So you followed the same rules, and it feels like a coin flip here. Like, was there even any useful information in there, or are we just flipping the coin week on, week out? So, two forecasts looked reasonably similar, weeks apart, verified wildly differently. What are some things that we can do to help forecasters. Today, I'm going to show a couple of tools that we've been sort of working on with what's called a linear inverse model, a LIM. I'll explain what that is in a minute. And we're going to try to do two things here. We're going to construct a LIM and then use it to create what we're called a dynamical filter to separate out predictable signals, stratosphere, SSTs, MJO, from unpredictable signals. So this is weekly synoptic variability, right? So all the things that we're trying to forecast in 452 on the daily timescales, that all gets put in the for the most part, gets put in the unpredictable bucket, and we're trying to separate that out. Also, I'm going to use the LIM to define a signal to noise ratio, and we're going to try to identify at the time of forecast what we would call a forecast of opportunity. This is where we're saying at the time we issue the forecast, do we have an expectation that this is a high-skill forecast or not? All right. So there are a couple different ways to, a linear inverse model has a linear. What do I mean by that? Well, there are a couple different ways to derive a linear model. The way that probably most people in here are used to is the way that I was used to. This kind of thing that you do in AOS 311, right? Like linear perturbation theory, or asymptotic analysis to derive the QG equations, right? You assume nonlinearities are small, and then you linearize the equations, and then you assume a plane wave solution, and you do analysis that way. Here, what I'm going to do is I'm not going to actually linearize the equations, but I am going to derive a linear model. Here, the assumption is different. Here we assume that the nonlinearities are rapidly decorrelating, and that when they are averaged over many periods, they start to look Gaussian, right? So this is just the central limit theorem. So what does this mean? This means that if I take daily variability, all stuff that's you're looking at on a weather map on a daily, daily, sub-daily timescales, if I integrate over several periods, a couple of weeks, those statistics are going to start to look Gaussian and random, temporally white, Gaussian white noise. What's left over, hopefully, are the more predictable signals, things that vary on weekly timescales. Buried in that are the things that we're going to hope to mine and try to understand. What does this go back to? So this kind of idea is not new. So you go back to Klaus Hasselmann, he's one of the, right? So he's one of the two folks in atmospheric science proper, right, that have won a Nobel Prize. He had the idea, and here I'm putting in red, these are quotes from his classic paper in 1876. And the assumptions that he was making in his, when you say stochastic, when I say Gaussian white noise, this is a stochastic model. He was making assumptions that we're going to make today, which is that the timescales of weather in the climate system, here by climate I mean things like MJO, and so are well separated. And what that allows is it's the assumption that the daily weather variability is rapidly decorrelated. Okay? Also, we're assuming that slow changes in the climate are the integral response to that continuous random excitation by the weather, right? So you have this bubbling of randomly exciting daily variability, and it's kicking these climate modes off, and that's the kind of thing that we're looking at. And this, if you look at statistics, right, so this integration of a white spectrum weather noise, this yields a red noise, or a red spectrum climate system, which is in agreement with observations. So this goes back to all the way to 1976. Here, he was not building a LIM, but here we are, and it kind of relies on those same assumptions. Here, we are modeling the timescale separation, as I mentioned, by slow timescale processes, and we're going to calculate our forecast operator is this L forecast operator, and that explicitly models all of the things that of interest on weekly timescales that we're interested for subseasonal variability. All of the fast timescale stuff, that's sub-weekly, is going to be parameterized, so to speak, by white noise. But that is observationally constrained, right? So this isn't just a random white noise. You calculate this from the statistics of observations, and so it is observationally constrained. So it is meaningful noise, despite the fact that we're modeling it as Gaussian and white. So how do we do this? This is an empirical model. So we take reanalysis data, say, error interim or something like that, and the first thing you need to do is decide what variables you're going to include. And there's a bit of an art to this. So what do we want to, you need to include things like, we want to forecast 2-meter temperature, 500 millibar heights, because that's what forecasters need in this case. But we also want to make sure that we're explicitly putting in things like MJO or ENSO. So here I'm including tropical heating and sea surface temperatures, and I want the stratosphere in there, so I put in a stratosphere stream function. There is a bit of an art to getting this right, so that you have a model that you can build a filter like I'm going to describe later that works well. You truncate those variables using EOFs. The EOFs don't matter, it's just that you need data truncation because you can't model all of the variance. You need to truncate the variance. Hopefully maybe you keep 50 to 70% of the variance. All of those EOFs get stacked into this state vector X, and then L, the forecast operator, is calculated from lag covariances of those variables. And here the training lag is a 5-day lag. The white noise is calculated also via fluctuation dissipation relation. I don't want to get into the technical details of that. That is also calculated from these same statistics. All right? So this is trained, this is this is machine learning, just in a linear sense. You're just, you've got training data and you're training a linear model on that. You can use a LIM as a dynamical model, so you can run it as a forecast model, which we do all the time. You can also run it as a climate model because you get statistics of the observation of constrained noise, and you just pick it and you can run it out for 3,000 years as a climate model. And the statistics that you get match observations really well. They match observations better than CSM does. It's a really nice stable model. I'm not going to use either of those today. I'm going to work with the forecast operator L for both signal to noise ratio calculations and the filter I'm going to talk about. So how do we build, so non-normal, anywhere that I forgot to take this, I was trying to scrub this technicalities, but when I say LIM dynamical filter, a stand-in for that word is non-normal. What does non-normal mean? That means all of the eigenmodes that I'm going to talk about, they can constructively and destructively interfere with one another. That's a really important feature. Why? We need to be able to, as the MJO moves through and ENSO moves through, these things have patterns over North America that project onto one another, and they constructively and destructively interfere. And that's what we're trying to separate out so that we can cleanly separate out those pieces and understand where our predictions are coming from. What are those anomalies coming from? Because ENSO has a different limit of predictability, and MJO has a different limit of predictability. They have slightly different patterns, and that's one of the things that we're after. So when you take this forecast operator and you do an eigen decomposition of it, it gives 3 very important pieces of information, 2 of which I will just very briefly talk about, and the third, which is also very important, I'm going to skip over. I have slides after my conclusions, and if those with the initials of Dan Maimon are interested in those, we can talk about them after the talk. Period and frequency of oscillation and the e-folding decay time come from the eigenvalues of this eigen decomposition. And what I have done here is I have plotted, in this LIM there were, I don't know, maybe 80 PC time series, so 80 eigenmodes, and each of them come with an eigenvalue. And I have plotted all of those eigenvalues on this axis in terms of the e-folding decay time, so that's how long they last before they die, and in terms of their frequency, that's the x-axis. And what you see here is they already naturally kind of fall into 2 groups, okay? Along the bottom axis in green is what I have misspelled with synoptic variability, somehow it was one word. That stuff, they all have short e-folding times, right? Less than 22 days. They decay very rapidly. They have no SST signature, okay? And they are purely atmospheric modes. They've got nothing to do with the ocean, so they're not long-lived. So they're dominated by tropospheric variability, and they are, for the most part, not predictable, right? They're dead by 22 days. So if we're interested in things 3-4 weeks, they just don't last long enough. The other grouping that I have highlighted in blue are what I'm calling stratosphere SST modes. These all have very long e-folding times. They all last longer than 32 days. All but one of them has joint ocean atmospheric components to it. So these are joint atmosphere-ocean modes, okay? Then there is one purely stratospheric mode that has absolutely no SST component, and that models extremely well, and I'll show that later, things like sudden stratospheric warmings, for those of you who know what that is, and I'll bring that up. These modes are reasonably predictable. All right. So what are we going to do? What I'm going to do is I'm going to take any anomaly that has all of these variables, bottom left, and I can take that and I can do one of two things with it. I can project data onto it, and I can use the lim as a forecast model, and I can filter it into these four components. Or I can take observations and like verification data. I can project it onto these, and then I can filter them to see with the forecast verification what actually happened. We do it for forecasts. I'm not going to show that today. I'm just going to show observations to get a kind of feel for how this works. We are currently working on building this out for forecasts, for the operational forecast models. But I just wanted to give people a flavor of what this is. So I am splitting this into weekly synoptic variability. This is, again, that's largely unpredictable. That's the bulk of the power. If I show you a power spectrum of this, that's almost all of it. So, when I showed you at the beginning of the talk that forecast skill is 0.2, 0.3, that has to be the fact, because if these other modes that we think are more predictable had more of the power spectrum, the system itself would be more predictable, but it's not. So in general, most parts of the anomaly live in that space. Then we have the MJO, and then we have coupled atmosphere-ocean modes. That's what I call the joint SST stratosphere modes. And I put stratosphere there because these teleconnections they arch up over the tropics. They go through the upper troposphere, lower stratosphere, right? So they have a strong projection in the stratosphere as well. And then we have a stratospheric mode, which is captures downward influence from sudden warmings. So what do they look like? Do they look like what we're expecting? Yeah. So here is the MJO phase 3 properly cited to Steph. And there, as I was right, so 250 hectopascal geopotential heights, and precip in the colored contours, and in the lim, I don't have those exact variables, but I got 500 millibar heights and tropical heating, and that particular eigenmode has an e-folding time of about 21 days. If you're someone who works on the MJO, you know that the MJO, that's about how long it lasts. As far as having large amplitude, and its period is something like 52 days, which matches observations as well. So this works out rather well. There are a whole bunch of papers, including by folks in the audience that have worked on this. So we have that one pretty well worked out. What about the stratospheric mode? For those of you who come from the stratosphere, you've probably seen this upper left plot. People call it the dripping paint plot. This is real popular when I was in grad school. Essentially what that is it's the northern annular mode, Arctic oscillation, whatever you want to call it. And that's averaged over the pole. And then following weak stratospheric events, you're seeing the downward propagation of, like a sudden stratospheric warming. You're seeing the downward propagation in the northern annular mode. And at positive lags, right, that's the influence from the stratosphere. So when people are talking about the polar vortex and colder outbreaks and sudden warmings, this is what they're talking about. However, not all of that red that you're seeing there is actual influence from the stratosphere. There is a lot of internal variability in this troposphere that is rapidly going back and forth. So you're seeing constructive and destructive interference. The influence from the stratosphere is actually more constant than that. Matt Newman and I have a paper in 2021 that we go through this. And a lot of that red, the stratospheric signal is actually, as much as I want it to be that strong as a stratospheric dynamicist, it's not. A lot of that red in the troposphere, in the stratosphere, the red is the stratosphere. Like that is the anomaly from sudden warming. But in the troposphere, a lot of that red is unrelated constructive interference. And then when there's destructive interference, that's where you see not a lot going on there. So bottom left, I've taken the lim filter, and the bottom left is a composite that's similar, has similar events to the one in the top, and you can see it's quite strong. But then if you filter it to just include the stratospheric component of that, you see that the tropospheric signal is weaker. And if you run the limb out like a climate model and you do this for the number of, there's a lot of sampling there, and you do 3,000 events, essentially you get a nice strong signal all the way from day 0 out to day 50, and it's just very light yellow. And that's kind of statistically what you expect. It's a signal that's for sure there, it's just weak. And both the limb and observations show that this gives you a negative NAO anomaly. All right. And with that NAO anomaly, you get a temperature anomaly over North America. That's why forecasters are interested in it. All right, so how can we use this filter to look at operational outlooks? So I'm going to consider two cold air outbreaks, one in 2021, and one in 2024. And I'm going to apply the filter to kind of contrast the impacts from the different climate modes. And what I want people to take away from this is the constructive-destructive interference patterns. And really the important part to keep in mind here is that if it's really a forecast of opportunity, it's going to be something that a forecaster can really lean into and adjust probabilities upward because you're sure about it. You're going to need constructive interference amongst at least 2, if not 3 of the predictors. Because as I mentioned, the synoptic variability has all the power. And you can have all 3 of those predictors, or one of them, pretty strong, and you can just get wiped out by the unpredictability of the synoptic variability. That's a coin flip. And so you got to be cognizant of that. You don't want to lean into the forecast unless you have several constructive interference reasons to think that you've got a forecast. So in February 21, I don't know if anybody remembers this huge cold air outbreak. Texas got smashed. Their grid was offline for a long time. It was very, very cold. On the left, I'm showing the forecast. It was a pretty good forecast. It didn't get Texas, so Texas probably wouldn't be happy with that. However, if you're a dynamic forecaster, this was a pretty good forecast. Like you were getting the pattern all right. So what were we locking onto? I was in this forecast discussion, and there was a lot of talk about several things. They didn't have this map, I should mention. We were working on this, and Matt Newman and I had just started showing up to these forecast discussions, and we're getting to know the forecasters. And after this was over, we wrote a paper on this cold air outbreak, and that's where these figures are from. And we still don't have something to deliver to them yet, but we're still working with them on it. So what I'm showing are the verification anomalies. So, right, if you look on the right, here's the verification. Cold, real cold everywhere. What I have done is I have filtered both the geopotential heights on the bottom and 2-meter temperature into the 4 components that I talked about. And you can see the weekly synoptic variability, which, by the way, it's just not going to be predictable. That's where the bulk of the power is. That's a saturated color scale, as you can see. That's where the largest part of the temperature came from. And that is just the way it is. That's to be expected. However, La Nina, the MJO, and the residual effects of a sudden stratospheric warming all gave strong, predictable contributions to this. And our argument in this paper was we actually were producing a limb forecast at the time, and we saw this. And if you read the forecast discussion, 2 weeks before, they didn't lean into this. And then at this forecast window, we were just like, we think this has been steady in the limb. We think this is pretty good. And they started pushing, the guidance got pushed in this direction because of those, in part because of those discussions. Also because Dan Collins, the forecasters are really good, is one of their better forecasters at CPC, and he was thinking along these lines too. So what you can see here is this, if a forecaster had seen this, if we had projected this onto the forecast models and they showed something like this would have been something that they could have been like, yeah, I feel confident about this. All 3 of my predictors are showing this. Even if I don't know what the weekly variability is going to look like, this is as good as it's going to get, and I'm going to lean into this forecast. All right. A few years later, there was a cold air outbreak. This is the one I showed earlier in the talk that was a total bust, right? Forecast showed temperature outlook of warmth that was due to ENSO going on, and it was a bust. So here, I'm showing the observations. This is what actually happened, filtered. Again, the weekly variability dominated. That's what caused, for the most part, that's what caused this cold air outbreak. In this other case, those other contributions were quite important to the depth of that cold air outbreak. Without ENSO, the sudden warming, and MJO, the cold air outbreak was not nearly as bad as it was. However, this one there was a little bit from the stratosphere, but it was mostly in weekly variability. The El Nino that they were forecasting and expected was right. Like, that's in the data. And the MJO as well. The problem is that between the stratosphere and the weekly variability, that just got swamped. And it didn't matter that ENSO signal was really strong. This is, if I was a forecaster and they saw this, and we were working with someone, they look at this kind of thing, this is useful information to them. They might not completely back off of that forecast because ENSO is still there and it's all you have, but they're certainly not going out on a limb like this, 70 to 60%, they don't often do that. That's very rare. They almost certainly, if they look at something like this, they're gonna hedge their bets and pull back on the probability guidance. So these are the kinds of things, yeah?
But this is a verification.
That's right. What happens when you put the IFS and project it onto here and you look at it? That's a talk for another day. That's where we're headed.
I'm just saying, like, this is, like, in retrospect, like,
100%.
you can look at that.
So
and say,
we get these forecasts from the LIM. And so we do have a LIM forecast that does this in real time now. However, it's a statistical model. They do use statistical information, no doubt. However, modern forecast guidance is without a doubt built on the ensemble prediction system from the operational models. So what do we want to do? We need to build this so that you have these variables in real time. And I know it sounds simple, but getting all the variables that are in a LIM like this in real time from the operational centers so that you can project it onto a state vector like this and filter it is a non-trivial leap. But that is where we're headed because that's what we need to know. I'm not convinced. I've done this for the MJO. We have already done this with the IFS for the MJO. And even the IFS, which is an awesome model, MJO doesn't look right. So it's going to be a whole can of worms understanding how to interpret that. But that is a direction we're headed because this is going to be useful information for forecasters. All right, let's see here. We're getting pretty close. I'll try to just spin through this couple of slides and then we can go to questions. How else might we objectively identify forecasts of opportunity? Well, in the LIM, as I mentioned, it's a clean split between predictable dynamics and forecast uncertainty, that noise, unpredictable sub-weekly variability. We can take those two pieces and we can calculate a LIM signal-to-noise ratio and then this thing that we call expected skill. All right? This, you get a number or a map of expected skill, and it is forecastly dependent, so it might look different. If I'm at forecast for December 1st today, the expected signal-to-noise ratio for a week 1 forecast and a week 4 forecast are going to look different. But what it's telling me is it should, if it's working right, it should take all the forecasts I've had in the past and in real time, and it tells me how high that signal-to-noise ratio is, and I can tell based on how high that signal-to-noise ratio is on whether I think it's going to be a skillful forecast. All right, so I'm just going to show this real quickly for the NAO. Right, this is just for those who don't know, you can define the NAO in a bunch of ways, but here I'm just defining it as the first EOF of geopotential height over the North Atlantic. Right, it's just a north-south shifting of the jet, and you can get a time series of the NAO, and that's what I'm going to show prediction skill for. All right, so what have I done? I built a LIM. I calculated that signal-to-noise ratio for 20 years of hindcasts. And then I calculated the signal-to-noise ratio, which, to be clear, that is information that I would have at time of forecast. And I calculate that signal-to-noise ratio, I group it, and I take the top 10, 15% and the bottom 85%, and then I calculate the skill for each of those, and I do it for the LIM, and I do it for the IFS. And why do I show it for the IFS? I show it for the IFS to show that the signal-to-noise ratio that we're calculating it's not just an artifact of the LIM. It is identifying something about the actual observed climate system that matters insofar as the LIM gets it statistically and operational models gathered. And what we see here is that for those top 15%, we indeed, those are the thick lines for both the IFS and for the limb, the correlation still stays above 0.5, which as I mentioned is kind of the magic line for something being useful, and it stays above 0.5, maybe even 0.6, all the way out to week 4 before it drops off. The dashed lines are the other remaining 85% of forecasts. And there you can see that after week 3, or after week 2, you're dropping below 0.5. And so that's the remaining forecast. That in a nutshell is why forecast skill is 0.3 on aggregate, because the bulk of the forecasts have essentially, it's a coin flip. There's no skill there. It's just random. Except for those like 15% of forecasts. And that's the name of the game, is be able to identify those and say, when I have one of these, I'm going to lean into that guidance and I'm going to up probabilities. Can we connect these to the physical modes? And the answer is yes. We took these same forecasts and we applied the filter to them, and we put the internal subspace is what we were calling the weekly synoptic variability. You can see that that gives almost no skill. And almost all of the skill is coming from those, so the green line is like 70 some of the eigenmodes. And the blue skill, that's where I just take the initial conditions in the limb, and for those like 8 eigenmodes, and I only keep that part of the anomaly, and I march that forward, and that's where all of the skill from those high signal noise ratio events come from. All right. With that, I think I'll just leave these conclusions up here, and I will move on. And thank you for your attention. I appreciate it, and I'll take questions.
Great. Thank you, John. As usual, we like to start with student questions. So if any students have any questions, please go ahead and raise your hand.
This talk was a student motivational talk because they need help. They can't build tools and be operational forecasters at the same time. And what they really need is they need people to build relationships with them. People in the forecast office every year have people, they get grants, and they come in there and they don't really talk to the forecasters about their needs. They get a grant, they build a tool, and then they come to the forecasters after the end of it and they go, I just designed the most earth-shattering thing. You got to use this. And then they give it to the forecaster, and the forecaster's like, I don't know what to do with this. And that happens every year through all the grant cycles. And what they really need to do is people need to build relationships with them so that you can work collaboratively with them to build tools that they can actually use. And that was sort of the goal of this talk, was to motivate all of you students to come up with ideas that can help them make these forecasts, which is really hard to do. I'm glad I'm not signing my name on that byline every day, because they have to, and they get scored. Yeah?
It seems like the kind of, what you're suggesting is the main forecasts of opportunity are where you can identify constructive interference.
Yep.
So do we know the amplitude of that constructive interference relative to synoptic variability?
Unfortunately, yes. Right? This is a game of shifting probabilities. Having La Nina, the MJO, say you had this, you don't have this weekly variability. That you're just not going to know, probably. It's in the limb, it just goes away. It's possible that we'll get a little bit of it. The limb, assumes that synoptic variability is noise, so it's a little bit limited. It's possible that at week 3, the forecast models might get a little bit of this weekly variability. But really, say you had those right 3 panels, you knew all of them. That's a really strong anomaly, all constructive interference. You're happy about it. It doesn't mean you're not going to bust. Why does it mean? You could get, I guess I don't have an example. You could get a warm anomaly on top of that just busts you, and there's just nothing you can do about it. One thing to keep in mind is we assume that the synoptic variability, I said it's stirring these modes. It's possible that Gaussian white noise has structure in it. And I think there are probably people here that, I heard today stochastic optimals. And it's possible that even though the limb assumes these things are all independent, that the noise preferentially stirs some of these things. So it's possible that even though the limb doesn't know that these things are related, that the noise that excites these things preferentially does this too. We don't know that yet. And until we do, the best you can do is constructive interference, and that's helping you shift the probability of a cold air outbreak. That's what you're hoping for. It shifts that risk up. It's still a probabilistic forecast. You still can get burned, but it's definitely way better than, and you know, it seems to work for 15%. The other 75%, there's probably not a whole lot you can do. That may be an intrinsic limit to that. Though Greg Hakem recently published a paper that says it's like, I don't know, 4,000 years. But 30 days, I'm teasing. You should read his paper. Does that make sense? Did you have a follow-up to that?
Yeah, so kind of a follow-up. So does that mean there's not really any talking between the mean state and the eddies and the limb? If your modes are independent from one another, then the synoptic variable, can your low frequency modes push the synoptic variability?
That's sort of implicit in this. So that is when Hasselmann writes, it's the climate is the integral response of the weather. What you're saying is something like, you can think of it like this. I have a La Nina. I have a ridge that's building up, kind of statistically speaking. There's a low frequency ridge, whether you can see it or not. You might have synoptic variability going in and over the top of that. And that's the thing, you can see that in this pattern. Even though this was a cold air outbreak, the total pattern was totally cold, right? That's what verified. This was there. That was there, okay? What you're sort of hoping is that if you have a La Nina response, statistically speaking, the waves, right, it kind of perturbs the jet north, and those waves are going to ride that, and maybe there's more variance, they're going to break more. And it's the aggregate response of that integral response of that is what we're trying to model. The limb is assuming independence, but that it's the averaging that gets you there. We're trying to average that out and look at the integral response of that low frequency stuff. Dan?
But those are separable, and that's like the limb does not, unless you put some sort of state dependency in there. I understand what you're saying, that some part of that, but in the limb world, based on what you're showing, those are separate.
But that doesn't mean they are, right?
In reality, you're right, but the limb is unable to
100%.
Yeah.
Well, sort of, right? Because
Yeah, but I mean,
the noise may preferentially, the limbs, mathematically speaking, they're independent. The limb, they do not, the modes don't know. However, the noise is observationally constrained, and it could be the case, that's why I bring up stochastic optimals. There could be structure in the noise that is preferentially exciting these modes. The limb doesn't see that, but if you do a composite on it, you might be able to see it. We just don't know. But that's an excellent avenue of, that is a big question.
yeah, sorry to jump into that question, but I mean, it seems to me like that's one of the more promising areas of
100%.
to move beyond this and S2S forecasting.
I would love to see someone study the noise in this. And John's like, I study the noise?
That's all I do. If I could ask a question, I don't know if I'm out of turn.
No, rock and roll.
Thanks, John. Really interesting presentation and some really cool stuff going on. What if you were to stratify your high, what do you call them?
Signal
Forecast
noise.
of opportunity events. They can't all verify. They can't all really end up being opportunities that are realized. Is that correct?
No.
Okay, so what if you look at those that don't verify or that do not end up being actual forecasts of opportunity? Are those the candidates where the noise might be particularly rich for investigation?
So I would say that I don't know. We have a really cool figure that I never put in here because it's hard to explain, where we stratified by signal noise ratio, and then we lined it up on an axis. And what you see is that for those high events, they're all high skill, except for a couple. Then when you get, and then you start stratifying, you go down the thing, and it's like a ball of marbles falling out, and it's random. They're just totally random. You're right, there are a few that are low skill, even though it says high expected skill.
Yeah.
If I were to guess, I haven't investigated those, it'd be useful to understand. My guess is that, I mean, the limb could have error in it. It's truncated in variance, so it could be missing some of that. My guess would be that the sub-weekly internal variability is like particularly strong or something like that, right? Because it's a ratio, right? You're hoping that those constructive patterns move the needle enough that it rises above the noise of the coin flip. And sometimes you might just be unlucky, and yeah, my guess is I mean, your favorite object of study always wins. Like, it carries the power. And so you're always kind of swimming upstream on that. Now the question is whether, there's never any doubt that that's the case. The question always is it predictable?
Yeah.
And that's the problem.
Or what about this question? Does it emerge from a characteristic state? Does the singular event in the noise emerge from a characteristic state in those failures?
That's an excellent question. I mean, we don't know. And as Dan was saying, studying the noise forcing, that's one of the things that we want. You're going to probably understand something about the excitation of the predictable things as well as the unpredictable things. And that's a really rich area. If I had time to do that, hint, hint, graduate students, that would be an area that I would really focus on.
Okay, thanks.
Go ahead. I'll move this way. How about that? Yeah, please.
That's super cool talk. So you mentioned that you're basically hanging out with the forecasters every so often.
Every Friday morning
Every
I
Friday
show up.
morning. So do you have any insights or like over the last 3 weeks or so as we've had this, what seemed like good forecast for this really rare substratospheric forming, any insights on how the forecasters have been thinking about that or what you've learned over the last few weeks? It seems like a very unusual situation.
So the first thing I'll point out is, look at the sleight of hand I did there with the color bars on the left 2 panels and the right 2 panels. My favorite child, the stratosphere, has half the color bar of the other ones there, right? MJO too, and I love the MJO, but I gotta tell you, any MJO people out there, the MJO is just a hard problem because you know what the problem, at least with the stratosphere and ENSO, it's stationary for the most part. The MJO, if you get the propagation off by like 2 days and it goes a little faster, it's out of phase, and instead of being cold, it's warm, and you totally messed your forecast up. The stratospheric thing, yes, they talked about it on last Friday morning. They talked about the fact that it's possible that, I don't know, I haven't looked since Friday morning. Is the sun warming going to happen? Anybody?
Maybe.
Maybe?
It's still maybe. It's like 50-50, but if it
Yeah.
does, it's for like 2 hours. It's
Yeah.
like barely dips below 0.
I'm not sure whether, from a dynamics perspective, I'm not sure whether this early in the season it's going to matter. Like, what is it's a dynamical event, right? So in the middle of the winter, the jet's very strong, you smack it, and I've written papers on it. I don't think it's from anomalous tropospheric activity. I think it's like you give it a little bit of the thing and there's an internal feedback and whatever. But you start out with a really strong jet and you go down. That anomaly and the Eliason relaxation that goes with that, adjustment that goes with that as it comes down is really strong. Right now, the vortex is just kind of weak, and it's just spinning up in the season, and so you cause it to kind of weakly go across. It's this weak little warming. I don't know if that's going to give the canonical cold event that you're expecting. I don't know. La Nina, so cold, La Nina should give you some cold, although it's early season, and the stratosphere, I mean, they're leaning into the cold, because I think that they're looking at this and thinking cold. I am harping about the constructive-destructive interference here. I won't lie, not all forecasters are created equal, and some of this message really resonates with some and not with others, just based on different backgrounds and things like that. So I don't know. The forecast last week, they were leaning into cold. I don't know if you saw the weeks 3-4. I don't know what's going to happen this week. Andre?
Yeah, I have a question, a little bit, so motivated by this discussion, but other early season heat vortex events tend to lead to more cold for North America
Do they?
than midwinter ones. So that's interesting. But I'm wondering if you're, like, can we learn anything from the modes that are embedded, like your SST stratosphere La Nina one? So the early season heat vortex events from previous years have been associated with wave reflection events, and it's really the wave reflection event that's sort of like a, week-long, maybe 2-week-long event.
That's not predictable, probably.
Well, it's somewhat predictable. It's because the NJO is in the phase it is, it's more likely
To occur,
So
sure.
I think-
Shifts in probability. That's what I was talking about with the QBO.
So
Yeah.
I'm wondering if that's embedded in some of these, like you call them SST stratosphere modes. Like, can you learn about the atmosphere by investigating these modes?
So that would be like a state dependence question, and the LIM does not have, it is state independent. To do a state dependent LIM, you need a lot more data. It's, training data, because you need to do this is what's called an additive noise model. You need a multiplicative noise model to be able to do state dependence. That said, I think you could probably learn, I think that you can dig into that stuff, and I think it is worth digging into. Matt and I wrote a couple of papers on the stratosphere, and then we have dropped it and haven't gotten back. I've been trying to get a student interested in it, because I think there's a lot of rich information in there. I would point out that it's not just cold air outbreaks. If you run this filter in real time, positive NAM events, the stratosphere, there are warm anomalies for sure. You just don't see them because they're covered up by other stuff. The question is back to the discussion with Dan, is whether, are there preferential forcings from the synoptic variability that are preferentially exciting these things? And even though the LIM sees them as independent, they go together. And we did that. I just had a paper with a colleague with the NJO, and we find that we have two modes that you need to explain the NJO. I showed it as one, but we just published a paper that showed that it's about to be published, that it's actually two. They preferentially show up together. The LIM can't have that. Mathematically, that's not a thing. But the noise must be preferentially exciting, and that perhaps could get at your question. Actually, behind you, Michael, and then, yeah.
So, first question is how, you're kind of arguing that the noise is much larger than the signal. What sort of signal to noise ratios are you looking at? What's that upper 15%? Is it a signal noise ratio of 0.2?
Oh, yeah, it's not big.
Okay.
Because what John's asking about happens.
Right.
And for the most part, you're not, I encourage people to go look at what the ensemble guidance looks like at week 4.
Yeah.
And you're used to seeing these like in an up. I can tell you this,
You showed that.
it doesn't, the ensemble guidance most often looks more like this. So imagine this, but it's in the right pattern. So you're like, oh, I got an anomaly correlation of 0.6, and then you look at the anomalies, and that's because the spread is wide out of these time scales and it's weak. So we're talking about, this is really the game of shifts, small shifts in probability, changing risks of extremes.
And then the second question is, all your noise maps, when you do it with ops, they don't look Gaussian or random. There is a lot of spatial structure to them.
They are, if you look at the spectrum on weekly time scales, it does start to look Gaussian and temporally white.
Temporal.
Yes, temporally white,
But spatially, there's a lot of structure.
a lot of structure, very rich. So when we want to study the noise, that's the richness that we want to understand.
And those are projecting on some of these other
Gotta be.
modes. Okay.
They have to be. we know it's got to be the case with MJ. We don't know what they look like, but it's got to be the case because we get, like, if two of these modes keep showing up together in the same, like, phase, the limb can't know that. The only way that that happens is the noise. And even though it's Gaussian kind of white noise, that's not the climate system. Michael?
Yeah, just a quick question. And you're sort of trying to motivate students about thinking about some of these problems. You had suggested that there are opportunities, or there are opportunities you and Matt meet weekly with these forecasters to look at these events and look at the forecast. You know, NOAA has their spring experiment where they bring out lots of folks that are working on problems on much smaller timescales, like convective outlets, to sort of test ideas and look at models and look at what's the success rate.
Yeah.
Is there something similar for climate forecasting? Is there an opportunity for the community of limb studiers, limnologists, you might call them, not limnologists?
I call him a limnologist all the time to tease him.
Right. To come together, not just with limbs, but other tools that can be used for subseasonal prediction, to kind of test these ideas out. And maybe it's because it's not for a 1 month period, it is spread out over the year, right?
Yeah.
To have some, you know, maybe it's a virtual sort of gathering on these weekly or maybe monthly times to talk about.
So we have been trying to get up and running. We did it last year, and we're trying to maybe do it this year, though things are a little complicated. But we do forecast discussions once a week. When we do that, so the actual operational discussions, you got to sign a non-disclosure agreement and blah, 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 because nobody wants to be trading on information you know ahead of time. But after that occurs, and the forecast posts on Friday afternoons, we have been doing forecast discussions. John, you'd love it. And with that, often that attracts a subset of the forecasters to the crowd and then our group. And you know, if that could be something that was more community-wide, I think that'd be an excellent idea to is that the kind of thing you're talking about? Yeah, I think that would be wonderful to expose people to that. And then people get exposed to both researchers and forecasters and things like that. We should talk as a private citizen.
All right, thank you so much, John. Let's give him a moment.